Hi, my name is Jim Williams from Linear Technology, and I want to talk about a new low noise voltage reference we've developed, and in particular, how we verify that noise in the reference. We're going to be covering a lot of territory very quickly today. You can hit details at the end of the session in the reference. It comes in a variety of output voltages with very tight initial accuracies and very tight temperature coefficients. But the specification I want to home in on is this 775 nanovolt 0.1 hertz to 10 hertz noise bandwidth specification. That's a difficult specification to build, and it's a difficult specification to verify. Let's take a look at the test methodology we use to do that. The conceptual noise testing scheme is deceptively simple in appearance. The reference feeds into a low noise AC preamplifier with a 160 nanovolt noise floor and a gain of 10,000. This section feeds into a 0.1 hertz to 10 hertz filter operating at a gain of 100, which gives us an overall 0 to 1 microvolt equals 0 to 1 volt output. There are two outputs from this section and an overall gain referred to the input of 1,000,000. The first output is the instantaneous noise around to the vertical input of the oscilloscope. The second output is the peak-to-peak noise in a 10-second interval, which is set by the sweep gate output of the scope operating at a second per division for 10 seconds total. The devil, as they say, is in the details. This thing is difficult to execute. Here's some of the detailed noise test circuitry. The gain of 10,000 is enclosed within a shielded can, along with a reference, which feeds an input RC time constant equal to 0.1 hertz. This 1300 microfarad capacitor is no normal capacitor. You can read about it in the app note. That gets us our low frequency cutoff. We go into a pair of extremely low noise JFETs, less than a nanovolt per root hertz, which are single-ended at a gain of 10,000 and fed back. These normally would be quite drifty and would masquerade as low noise generators. We've got a DC servo keeping them honest up in here. Then we go through another gain of 100 filter section, 0.1 hertz to 10 hertz in these two amplifiers here, and from there we go to the peak-to-peak noise detector. Here's the peak-to-peak detector. It's pretty much conventional in operation. We've got positive peak here, negative peak here, FETs for peak detecting diodes for low leakage. We single end into a DVM, which also includes a strip chart recorder. And the instantaneous output is taken here. The timing for the reset is through this one shot, and the level shift from the oscilloscope sweep gate output. Now let's take a look at system performance. Here's a performance summary for the entire operation of the circuit. The first thing we do is put a microvolt into this thing to make sure we've got enough bandwidth in the noise detection circuitry to capture the full 10 hertz operation. We get about 10 millisecond rise time here, which corresponds to a bandwidth of 35 hertz, which is more than enough to catch all the action in the circuit. The peak-to-peak noise detector waveforms include the instantaneous noise in, the positive peak, the negative peak capture, the output of the peak-to-peak detector, which is the absolute value of the whole thing, and the reset pulse, which occurs every 10 seconds. The measurement noise floor, now this is the measurement noise floor, we haven't installed the reference yet, comes in about 160 nanovolts peak-to-peak in this particular 10-second sweep. This is a rougher test of the same measurement. It's about 6 minutes of peak-to-peak noise detection read out on a strip chart recorder, and the highest peak-to-peak value is about 150 nanovolts. We say 160 to stay out of trouble on specifications. Finally, we plug a 6655 reference into this thing and look at the peak-to-peak noise in this particular 10-second interval. Comes in around 150 nanovolts peak-to-peak. If you wait long enough, do 1,000 of those sweeps, you'll see peaks as high as 750, 760 nanovolts, and that's where I get my 775 nanovolt spec. Before we go, I want to say a few words about physical construction, particularly in the preamplifier. The preamplifier board is contained within a metal can, which has a roof on top of it, so it's fully sealed for shielding purposes. The preamp is powered externally by these connectors here. The reference is powered by a battery for noise considerations. This is the capacitor and the resistor, both of which are shielded, so that's a double shield for the input RC. This is the servo amplifier for the FETs. These are the FETs in this area here. This is the output amplifier. This is the back side of the same board showing the thermal cup. This board fits down into here and closes up. We haven't hit all the details. You can get those from the references listed at the end of the app note. If you've got questions or comments, you can call me directly or reach me through linear.com website. Thank you very much.